Now, any questions up to this point? We have the conductors. We put some charges on the conductors. They create an electric field and hence a potential difference between these two conductors. If you calculate or measure this potential difference, you will see that it will be proportional to the charge that you put on the conductors. And that proportionality constant, it will not depend on how much charge you put. And that proportionality constant is what we call the capacitance of the system as a whole. And we had made two examples. One of the most common ones is the parallel plate capacitor. Now, how many of you opened up some electronic device? Okay, there will be basically a couple of pieces that you will see. Some of them will look like this. They will just look like a cylinder. And some of them will just look like a small lentils. They will just look like this with some endpoints. They are quite flat, round. Both of these are the capacitors we have. Now this one, this cylindrical one, is in fact just you take a parallel plate capacitor, a large one, you just roll it. And that is how you get those cylinders. And to make sure that these plates do not touch each other, you put some insulator in between. Well, we will study the effect of the insulators tomorrow. But this is an example of an almost parallel plate capacitor. This one, you don't roll those things, so they are small. The area will be small, so the capacitance will be smaller in general. But again, you basically do the same thing. You just take two plates, two conductors, put something in between so that they will not touch each other. And that is your capacitor. Then, of course, they will be connected somehow. I mean, you can have one plate, another plate, just connect them. And you can still store some charge in them, creating some potential difference, etc. So that is what we will be studying now, connecting capacitors. Well, there will be mainly basically two different ways of connecting capacitors, the series and parallel. So first, let's look at the series connection, capacitors in series. So this is how we will be showing the capacitors. This is a capacitor with capacitance C. This is the symbol that we will be using all the time. This doesn't show the shape of the capacitor. It has nothing to do with the shape. It's just a symbol for the capacitor. Now, when we connect them in series, we just have this configuration. So if you just think of this as a parallel plate capacitor, you put some charge on one of them. Let's say plus Q. And of course, you have to put a negative charge on the other side of the capacitor. So this is a minus Q. This is our capacitor, which we can use these wires to put some charge and extract some charge. So we put some positive charge on this one and a negative charge on this one. Well, then we know what the charges on the other plates are. What is the charge on this plate? It will be negative, so this will be positive. So let's say we put a charge Q in this capacitor. So that means on the positive plate we deposited plus Q. On the negative plate we deposited minus Q. So here we have a plus Q charge on this plate and a minus Q charge on this plate. So the first thing, how much charge did we store in this capacitor? Now, how much charge, let me put it in a different way. When we say that we store a charge Q in the capacitor, we basically take some plus Q charge on the negative plate and put it on the plus Q from the one plate, put it on the other one. That is just the amount of charge we stored, let's say. We moved from one part to the other one, Q. In this one, how much charge did we move from one side to the other one? just Q. It's not plus Q, it's just Q. So Q should be equal to C times delta V. Let's say the C equivalent. Here we don't have a single capacitor, but still we can store some charge in this system, which will create some potential difference, and the charge and the potential difference are again proportional, and the proportionality constant will be what we call the equivalent capacitance. So if we would replace this system by a single capacitor, we should choose a capacitor that has this capacitance. Now, what is the potential difference between these two plates, these 2 points, this point and this point? The potential difference. What is that in terms of Q and C1? That's just Q over C1, because the definition of the capacitance is that if you put a charge Q on your capacitor, but the total charge is always 0, but whenever we say putting a charge Q, we put a charge Q on one plate and the minus Q on the other one. Whenever you put a charge Q on the capacitor, the potential difference between the 2 plates is always Q over C1. But by the way, this is the potential difference between the 2 plates. But here, Q over C1. Here I'm asking for the potential difference between this point and this point. Is it equal? So Q over C1 is the potential difference between this point on one plate and this point on the other plate. But now I am asking for the potential difference between this point A and B, let's say. Are they equal? Why? Why is the potential difference between A and B equal to the potential difference between, let's say, A prime and B prime? Why? Somebody else? Oh. Okay, why not? So you are saying that there's this capacitor, so it will change the charge distribution somewhere. It might affect the potential over here.
Well, we know that the potential depends on. Okay, the potential is constant on a conductor. So basically, it won't change because the wire is a conductor.
Why is the potential constant on a conductor? Electric field is 0, so the integral of the electric field over any path that remains in the conductor will be 0. So there is no potential difference between any 2 points on the conductor. So the influence, remember, if these are parallel plate capacitors, let's say, the electric field is non-zero only on the inside. Well, this is not infinite. There will be some fringing effect, so it will have some influence on the other outside points, but nevertheless, this point and this point, they are on the same conductor. Since it's a conductor, there is no electric field between these 2 lines along this conductor. So there is no potential difference between those 2 points. But don't get confused. If you consider, for example, the integral of the potential difference is the integral of the electric field. Instead of going through the conductor, you can just as well prefer to go along such a path, even go around over this one and go back to this point. Or just start from here, go around, go inside, and go to this point. Even for such a path, the potential difference will still be 0 because the potential difference is independent of the path. We are still in electrostatics. Nothing is moving. So we just put the charges there, they settle. That's it. It is? Yeah, they are full. We are not looking at the changes in the charges in the capacitor. That is what we will study next week.
How do we know that those inner plates gain the same charge?
Well, let's see. We know that out of these plates, the electric field is 0, right? Let me just consider such a closed surface. What is E on this surface? What is the electric field on this surface? 0. So the integral of the electric field over this surface, that is the total flux passing through this surface, is 0. But the total flux passing through a closed surface is proportional to the total charge inside. If the flux is 0, then the total charge inside should also be 0. So I know that I put plus Q charge over here. There should be a minus Q charge on the other plate. Other questions? Okay, so let's continue. What is the potential difference between the point B and D? Same? Q over C2. Because these 2 points, the potential difference between these 2 points is the same as the potential difference between the plates of this capacitor, because these 2 points and these 2 points are on the same conductor. So there is no potential difference between this point and this point, and there is no potential difference between this point and this point. And we know the potential difference between these 2 points, which is Q over C2, so that should be the potential difference between B and D. Now, what is the potential difference between these points? Between this point over here and this point over there. The sum of the 2. Because to calculate this potential difference, what I can do is just imagine any path, integrate the electric field over any path. So we can just start from this point up to this point. What is the potential difference? 0. From this point up to this point, what is the potential difference? Q over C1. From this point to this point, what is the potential difference? From this point to this point? 0. So the sum is nothing but the sum of those things. Delta V is equal to Q over C1 plus Q over C2. But this tells me that delta V over Q is 1 over C1 plus 1 over C2. But this basically tells me that delta V over Q is nothing but 1 over the equivalent capacitance. Any questions on this one? Now, another way to see this relationship is just imagine that these 2 capacitors are just identical parallel plate capacitors. So we have this one and then the other one. This, let's say this length is L1, L. Let's say L1, and this is also this is L2. They're not completely identical. L values are different to make sure that they have different capacitance. So they have the areas A and A. C1, if you remember the expression of C1, that was epsilon 0, A over L1. And C2 is epsilon 0, A over L2. Now, this difference over here has no effect. There is no electric field here. There is no potential difference between this point and that point. So the same thing I can just imagine as this system. This is L1. This is L2. A and A. And remember, the charge over here is plus Q, the charge over here is minus Q. So this one is just the sum of these two. So the charge on this one is 0. So it is as if it doesn't exist. So this is equivalent to this one, which is equivalent to this one, with the separation being L1 plus L2. And you see the capacitance is inversely proportional to that length, or 1 over the capacitance, 1 over C, is proportional to that length. So if you increase the length, you increase 1 over C. So this automatically tells you that 1 over C equivalent, which is proportional to L1 plus L2, but L1 is proportional to 1 over C1, and L2 is proportional to 1 over C2, the proportionality constants being equal in everywhere. So effectively, connecting capacitors in series is just similar to increasing the length between the plates. No, this one is theoretically correct. If you have two capacitors, there will always be this difference in length. But since there is no electric field over here, if I calculate the potential difference, it won't make any difference if I imagine that I just move this capacitor all the way to this one. The potential difference between these two moved capacitors will be the same as the potential difference over here, because I'm basically removing this region which doesn't have any electric field. Well, the capacitor basically stores charge. A battery creates this charge difference using the chemical energy.
But we are using capacitors like batteries in some.
No. When we study batteries and when we start studying circuits, we will see that they behave differently. Another difference is, for example, in a capacitor, remember, Q is equal to C times delta V, or delta V is equal to Q over C. In a capacitor, if you use the charge in the capacitor, the potential difference between the two ends of the capacitor gets smaller and smaller. In a battery, the potential difference between the two terminals are constant, or almost constant. So that is the main difference. Between the capacitor and the battery. As you use the charge in the capacitor, the potential difference across the capacitor becomes smaller and smaller. In a battery, when you buy a 1.5 volt battery, you know that until it reaches its end, it will be almost 1.5. True.
But can we charge a battery by using capacitor?
If you have sufficiently enough capacitors, yes. But the problem is, okay, ask this question when we study circuits. Because you see, if you want to use if you charge a capacitor using a battery, eventually what you will end up is the potential difference across the battery will be just equal to the potential difference across the capacitor. Then there won't be any current. Nothing will be charging nothing else. So you have to increase the potential difference across the capacitor if you want to use it to charge the battery. Now let's also discuss this is the series connection. Let's discuss the parallel connection, and after which we can discuss whether we can use the battery, how we can increase the potential difference. In parallel. So let's say we have these two capacitors. Let's say this has capacitance C1, and the other one has capacitance C2. And we connect these plates by the same wire, and these plates by the same wire. And then we apply some potential difference between the two. Now, in the series connection, it is easier to think in terms of the charge given. In this one, it is easier to think in terms of the potential applied, the potential difference between the endpoints. So what is the charge on this capacitor? What is the potential difference across these 2 points? Now, I just connect these plates with the same wire, these plates with the same wire, and I apply a potential difference by some means between these 2 points. What is the potential difference between these 2 plates? It's the same, delta V. So what is the charge? What is Q1? This is, let's say, plus Q1, minus Q1. This is plus Q2. This is minus Q2. Q1 is equal to the potential difference across the plates we know, and the Q1, the charge on the capacitor, is related to the potential difference by its capacitance. Q1 is nothing but C1 times delta V. Of course, you can say that why doesn't this capacitor influence this one? Well, mainly the electric field is only confined inside the capacitor. There is no electric field outside the capacitor. What is Q2? Well, that is C2 times delta V. Now, to create this potential difference across this system, what you have done is you just moved some charge from this point, this plate, to this one. How much charge did you move? Q. The total charge you moved is Q1 plus Q2. And from the definition of the capacitance, this has to be equal to C equivalent times delta V. Well, Q1, we know that it is C1 times delta V, and Q2 is equal to C2 times delta V. This is equal to C equivalent times delta V. C1 plus C2, this is equal to C equivalent. So if you just combine capacitors in parallel, what you obtain is that the total capacitance is just the sum of the two. Now, we can also have a similar explanation to this one. In this case, let's just imagine that these two capacitors have the same width, L and L. But to create two different capacitance, we can just imagine that this has area A1, this has area A2. So if you just connect these wires, well, basically there's no potential difference between this point and this point. They are at the same potential. So we can just imagine we are just moving them closer. So this is A1, A2, this is A1. The thickness is L. So basically we are making a capacitor with the thickness the same, area the sum of the areas. And remember the expression for the capacitance. The capacitance is epsilon 0 times A over L. So since you are adding the areas when you are connecting them in parallel, you are basically adding the capacitances. So you can store more charge. Now, any questions? No? They are not empty. The conductors are just conductors. They are filled. But there are no currents running in the system. There is no electric field inside the conductors because they are conductors, not because they are empty.
You said that there is no current in this, but why isn't there connected with the wires?
Well, the wires are there so that they make sure that these 2 points are at the same potential and these 2 points are at the same potential. So we can talk about the potential difference between this system rather than the potential difference across this capacitor and the potential difference across the other capacitor. Now, of course, next week we will start studying circuits that contain capacitors. There we will have the currents. There we will assume that the currents do not modify these properties. Now let's see how we can increase the potential of a capacitor. Let's just imagine we have some means of creating some potential difference. Well, that means is a battery, but we will see batteries next week. Now, one way to obtain even a large potential difference is just using the battery without changing the shape of the capacitor, because in general the capacitors, when you go and buy some capacitors, they will be just closed boxes. There's nothing much you can modify there. But let's say you take tens of capacitors. You just connect them in parallel. Identical capacitors. You just apply a potential difference delta V. Let's say you have n of them. What is the potential difference across each one of those capacitors? Delta V is the same. Now you take these capacitors that have a potential difference delta V and connect them in series. And you have 1, 2, up to n capacitors. They're identical. So what is the potential difference now? N over delta V. Well, let's see. N over delta V, what are the units? Does it have the correct units for the potential difference? What's the unit of N? N is just number, no unit, 1, 2, 3. What is the potential of delta V? The unit of delta V? Volts. So this quantity has units of 1 over volts. So it doesn't have the correct unit for a potential difference. What is the potential difference? Well, here we have delta V, another delta V, another delta V, another delta V. We have n of them, so we have n times delta V. If you have n sufficiently large, even if you have a small potential difference, you can create a large potential difference by using this trick. So can you use a capacitor to charge a battery? Well, yes. But you have to do lots of tricks there. The chemical storage is much easier. Other questions?
I'm wondering if, for example, you have two capacitors, and then each one farad, another one 5 farad. In circuit, they already use the 1 farad capacitor. After finish that, what's your expectation? The 5 farad capacitor will give the any battery, recharge the capacitor, or what's your expectation?
Well, circuits, let's just leave them to next week. And in which direction will the current move? Let's just leave it to next week. This week we will be mainly studying the properties of capacitors. Now, how many of you have seen an old radio which has this tuning knob? Well, every year the number gets smaller and smaller. Well, do you know what that is? That's basically a capacitor. And that is a capacitor whose capacitance you can change. So basically, that device is nothing but layers and layers of plates. Well, let's just imagine 2 layers like this. These are the sizes. So when you change the knob, you are just changing the overlap area. So since you are changing the overlap area, that is basically the effective area in the expression for the capacitance. You are changing A, and hence you are changing the capacitance of the capacitor. And why does it change which radio channel you receive? That will be probably in 2 months, towards the end of the semester. Not yet. And another thing about the units, I mean, I do emphasize you about the units now that I have a graduate student in my office. I mean, if you have visited my office, you have probably seen her. She has been struggling with checking her units. And probably the mistake that she is searching for is because she didn't check, she has been trying to figure out for the last, 1 week. And she would have probably figured it out if she had checked the units the first time she had seen the problem. So units are important. They are just not nuisances, or they are not just the things that I insist on you. You will have to deal with the units all your life. Check them, know them. Okay, any questions? Why do we use capacitors? Well, tomorrow we will study the energy stored in the capacitor. If you think about all the technology that we are using, it is mainly manipulating energy. Just moving energy from one point to the other one, and that's it. And controlling how energy moves from one point to the other one. Well, here we have the capacitor. It is one means of storing the energy, and we will see that it will be one means of transferring energy from one point to the other one, or controlling the transfer of energy. Now, why do we use it? It will become more clear after, let's say, at least 1 month. Our next subjects will be circuits, DC circuits, direct current circuits with batteries. Then we will be using the capacitors. After that, we will start the magnetic field. And once we study the magnetic field, we will study the time-dependent currents, like the currents we have over here. Then we will see that these capacitors can be used strongly to control the current, to control which direction it goes, or which frequencies pass through a given circuit and which frequencies do not. If you are interested in music, are you? Okay. For example, in the radios, you have all these equalizers. They use capacitors. At the beginning, this one. Okay. This one. Well, this is related with the capacitance, and what is important is the capacitance. It is not the shape of this function over here, but we will see that it's the capacitance that is important, along with other things in the circuits. Well, for example, in music, if you want to, you have the high-pass, low-pass filters. They use capacitors. One of the things, at least, they use. If you connect your capacitor in parallel to your circuit, it doesn't allow low frequency to pass through. Okay, other questions? Yes? So this is our spherical capacitor. And the capacitance. An atom as a capacitor. Well, you can imagine an atom as a capacitor. Does it store charge? Can you add charge to an atom? I mean, if you can add charge to your system, then that's a capacitor. It stores charge. It stores energy. That's the definition of a capacitor. But again, I mean, for this semester, we are dealing with the classical, non-atomic. I mean, we will be describing the atomic picture, what goes in the atomic level, only superficially. We will not go into the details. For that, again, wait until your third year. Now let's do one more example before you go. Let's look at the cylindrical capacitor. Now let's just imagine we have two cylinders, one inside the other one. The inner radius R1, the outer radius R2. What is the capacitance of this system? Now again, we will assume that although it has a finite length, let's call it L, we will assume that the electric field this creates will be almost identical to the electric field created by an infinite capacitor. So what is the electric field created by an infinite cylinder? Let's just assume we have this infinite cylinder with charge density lambda. Let's say it has a radius R1. What is the magnitude of the electric field over there at this point? We start by a Gaussian surface. We know that the electric field should be in this direction. If you imagine this circle, the electric field everywhere will be horizontal and away from my wire. This is the direction of the electric field. So I can imagine such a Gaussian surface, which is another cylinder. Everywhere, the electric field is perpendicular to this area vector, perpendicular to the area, so it is in the same direction as the area vector. So this is equal to E times dA times sine theta, sine 0, cosine 0, which is 1. Because this dA vector, remember, it's a vector perpendicular to the area. Now we can imagine E dot dA over this closed surface. Now, of course, if we imagine this cylinder as a closed surface, we have the bottom area, we have the top area. We also have to take that into account. This is E dot dA over the top plus E dot dA over the bottom plus E dot dA over the side. We know that at the top, dA is pointing upward, electric field is horizontal, so E dot dA at the top is 0, because these two vectors are perpendicular to each other. On the bottom, dA is pointing downward, the electric field is horizontal, again at the bottom E dot dA is 0. This is the only contributing piece, and for this piece we know that E and dA, they are pointing in the same direction. Furthermore, we know that the electric field the magnitude of the electric field doesn't change on the side because it can only depend on the distance from the wire. So this is equal to E times the integral of dA over the side well, the area of the side of the cylinder, well, let's say this is a cylinder of radius r at the height h, E times 2 pi r times h. By the way, for me, this is a problem which doesn't involve any knowledge of integrals, except then what they mean. We didn't evaluate any integrals here. And we know that by Gauss law, this E dot dA should be equal to the total charge inside my closed surface. Well, this cylinder has lambda charge per unit length. A length of h is inside my cylinder, so the total charge inside, Q enclosed over epsilon 0, this is lambda h over epsilon 0. This is Gauss law, this line. So just equating the two, 2 pi r h should be equal to lambda h over epsilon 0. H is cancelled. I have an E over here. So E is equal to lambda over 2 pi r epsilon 0. This is the electric field of a cylinder. Per unit length. R1? So? No, lambda per unit length. Of course, you can also define the charge per unit volume in terms of lambda and R1, assuming it's uniformly distributed. But in this derivation, the electric field will be determined by charge per unit length. Now let's go back. We want the capacitance of the capacitor. So the procedure is same. Put some charge in the inner conductor. Let's say we put some charge plus Q in the inner conductor and minus Q on the outer conductor. The electric field the magnitude of the electric field in the region in between will be lambda, the charge per unit length, which is Q over L divided by 2 pi epsilon 0 times 1 over R, the distance from the central axis. This is the electric field in this region. Outside, the electric field will be 0. Inside, again, the electric field will be 0. Then the next thing, potential difference. This is nothing but E dot dr. Along the path, I can just imagine going along a radial line from the inner conductor to the outer conductor. So this will be equal to Q over 2 pi epsilon 0 times L dr over R from R1 to R2. This is my delta V. This integral. This is usually one of the favorite integrals of students. It's just a logarithm. So delta V is equal to Q over 2 pi epsilon 0 L times the logarithm of R2 over R1. And this, by definition, is Q over C. So Q's you can just cancel. We know what C is. By the way, if you look at the potential difference, remember at the beginning of the lecture I said that we usually set the potential at infinity to be 0. Let's just consider the case when the outer shell is at infinity. If the outer shell is at infinity, and let's just imagine that this is an infinite wire. That's an infinite wire with Q over L charge per unit length. If R2 goes to infinity, Logarithm of infinity is infinity. So the potential difference between a point at infinity and any other point that is not at infinity is infinite. That basically tells you that you cannot set the potential at infinity to be 0 for the case of the cylinder. This is one of the, let's say, one of the problematic examples. You cannot set the potential at infinity to 0. Also for the infinite plate, infinite plane, you cannot set the potential at infinity to be 0. But if you have some finite charge distribution, some charges over here, only in that case you can set the potential at infinity to be 0.
We also can't call it infinite.
It doesn't exist. I mean, it's just a point far away. Far, far away. Okay, any last minute questions? You cannot go yet. Okay, so see you tomorrow.